Hi everybody, welcome back. It's been a little bit since I've been posting videos, and the ones I have been posting have kind of been further apart than I normally do. But I am pleased to say, those of you who know, the surgery was a big success. I'm on the other side of it now. I'm doing well. I'm back to work, all those sorts of things. Just not allowed to lift any heavy objects or push or pull heavy objects for another 4 weeks. But all is good. You know how doctors are, they're always over protective. But anyway, thank you all for the prayers, for the well wishes, and for all the good comments. I really appreciate it. So what we're going to do in this video is I'm going to finish up this 700, this phase linear 700 amp. Actually, it is finished. We're going to just demonstrate it a little bit and go over some of the things that I did and how I finished this thing off. That's what I'm going to do first here, is I'm going to show you the schematic in its final form. It is uploaded along with the phase linear 400 amplifier schematic that I drew, or that I made. And they're going to be up on my Patreon channel, so any of you patrons can download it. But I will also put a screenshot of it up on the screen right now. Those of you who wish to do a screen capture and print it out, please go ahead and do so now. And then we'll actually look at the schematic a little bit and kind of explain some of the things that I did. Now, I did make some changes in the circuitry, but I didn't change the circuit's design. I only changed the values of some components, and we'll go through with you why I did that and what the results were. In other words, everything I did on this can be reversed. Everything I did on this, is just resistors, capacitors, and transistors. That's it, just changing their values. Sometimes I just changed the value of the resistor was the same, but its wattage was increased a little bit. Sometimes I changed the value of the resistor a little bit. In one or two small areas, I added a couple of small capacitors, and that was for kind of to control oscillation a little better. These things were known to burst into oscillation sometimes. You get parasitic oscillation. And by doing this, that settles that down a little bit. So those couple of little changes are in there. But again, they can be removed very easily. Heat them up with a soldering iron, pop them off, back to its oscillating old self. So let's take a look at it, and then we'll put the covers on and we'll demo it. Well, I was editing the video and I realized that the entire section I did on the theory of what I did to this, to the circuit and everything, didn't get recorded. And this happens to me sometimes because I am not a video person. I am a, electronics person. And a lot of times when you hit the record button on the camera, sometimes you don't push it hard enough. And if you don't pay attention to make sure it's recording, you sit there and you talk to yourself for 40 minutes or whatever, and you record absolutely nothing. And then when you hit the button to turn the record off, you're actually turning the record on. So then you have this big long video of you moving things around on the bench and doing nothing. So that's what we got. So we are going to do this all over again. Isn't that fun? Really what I wanted to do was just show you the changes. Here's the completed schematic. This is the final version. And like I said, I will pop this up on the screen so you can screen capture it. But I'll go over with you what I did. Anything that you see that's highlighted in red is something that's different from the original factory design. Now, it doesn't mean I changed the circuitry itself, but I just changed a value of a component, or like in this case here, I added these two components, and this component here, and this component here. But generally, if you look at the original design of the schematic, you'll see that it looks pretty much the same as this, other than these few changes. And I'm going to go over why I did this. So let's just start at the input and work our way all the way to the output. So on the input, there's a difference between the Series 1 and the Series 2. One of the differences is the input section on the older versions of these used discrete components. So the differential input amplifier was 2 transistors, very traditional looking. If you look at any of the Marantz or Pioneer or Sansui, basic input circuit where you have one Class A transistor that's your input. It's a no gain circuit. And then you have the other transistor for the feedback going into it, and they work together. I mean, you all know that. And in the later versions, they went to an op amp to make it simpler. And op amps are usually quieter, or, it's debatable. Some people are purists and they like the discrete components, but these work well also. The original op amp that was used in these was an LF356, and it was in a metal can, and they had a lot of problems with them because, number one, they drew a little more current in idle than some of the other ones that were out there, other op amp choices. And one of the problems is this thing had a horrible thump when you turned it on, because as this thing would come up and stabilize, you'd get this big loud thump on power up. So later on, they went to a LF351 instead of the LF356. It runs on lower current. In order to do that, they increased the resistance. These were 3.6K, I think, originally. This here and this one here, these two, R1 and R2. They increased them to 7.5K, and they were like a 5-watt ceramic resistor. And I just replaced these with a 7.5K metal film. They're just a little heftier, a little better. They're smaller, physically sized, and they don't burn up very easily. They're pretty good. Either one would work, though. It doesn't matter. Because mine was missing one of those because of that weird modification they did on it. So I had to replace them. So because you need less current, they increased this. Now, you could either plug an LF351 like they had in there, or what I had in stock was TL071s, and so that's what I used. It works just fine. They're interchangeable. These technically are a little bit lower noise figure, but if you look at the specs side by side, they're very similar components, so I wouldn't get all uptight. Some people do, but I don't. It's not that big a difference. On the feedback circuit, so the non-inverting input of the chip is your signal input, and I kept all this stock. This is the way it was from the factory. You have a switchable input coupling that you can have a capacitor coupled input. So if you have any kind of an offset on your input, this would eliminate it. If you have a zero offset, signal source, you can switch and bypass this, and that allows you to have a direct connection in there, and that eliminates any of the noise or any of the reactive component of that capacitor. So theoretically, it should sound better, but again, I don't notice any difference, but I'm sure there's those who will. And then in the inverting input, that's your negative feedback. Now, negative feedback does several things. The first thing it does is it'll reduce distortion, and it will reduce the overall gain of the whole amplifier. So by having feedback, the amplifier will have less sensitivity, input sensitivity from input to output, than it would if you didn't have feedback. But that's a good thing because it will clean up a lot of anomalies that happen in the circuit and reduce the distortion. The second thing that it does is it can make the amplifier's response more linear. And what do I mean by that? From 20 hertz to 20 kilohertz, where your hearing is, well, your hearing, not mine. My hearing isn't like it used to be. But anyway, the audible frequency range, if I put a 1 volt RMS signal in and I get a however many, whatever the gain is, out, it would be that same gain all the way across the board, whether you put 20 hertz or 20 kilohertz or anything in between. A lot of times, because of the components in the amplifier itself, all the capacitors and the transistors and so forth, that is not always going to be very linear. Even when you add that feedback, you lose linearity. So what you do is you put a filter network on your feedback. Now, sometimes they'll put it in line like this, and sometimes they'll put it in parallel to ground, like this is happening. And what this was doing was this was controlling the roll-off of the low frequency. And with its original design, which I think this was only 180 ohms or something like that. It was lower resistance than this. And what was happening was the amplifier would roll off at about 40 hertz. 40 hertz is a pretty low note. But if you wanted to hear that subsonic sound, it would roll off. And, by the time you were at 20 hertz, you were down, I forget how many dB it was down, but it was a good bit. That's great. Like if you're Pink Floyd and you want to use this on your gigantic speaker cabinets to do a live performance, you don't want all those subsonics, because those subsonics take up a lot of the power that this amp can deliver. And you can't hear them, and you're in this big open space. You really want to amplify the sounds that are more in line with our hearing. So that was a good choice for that design, because that's kind of what this amp, it's being such a large, powerful amplifier, that's kind of the applications you would use this. But if you wanted to use this in more of a home use, or, hi-fi, audiophile, I'm going to use that word, you want it to roll off starting at about 20 hertz, which is what this does. So by increasing this to 750 ohms, that moves that roll-off point down to about 20 hertz, and clear down to about 10 hertz. It's rolled off, but it's, you can get those subsonics, that bass that you feel. And I'm telling you, when you hear this amp play, the one that I just did, you can feel it. I mean, it's really, really a smooth sound, and it takes a little bit of the harshness off, at least to me, to my ears. This is a personal opinion, and to me, this amp, I can listen to it all day long. I mean, it just sounds so smooth. So anyway, one little change in a component value, it made a difference. We also I added these two bypass capacitors on your power input for the chip. So your positive and negative inputs, for your voltage supply is pins 4 and 7 on the op amp. And originally, they just used a shunt regulator. You're just sticking a Zener diode in there after a resistor, a dropping resistor. What would happen is, number one, that when the original design was 3.6K, there would be a lot of current going through this thing, just being wasted, so that you could provide the current you needed for the LF356. By going to an LF351 or a TL071, they were able to reduce this, the current here, put a bigger resistor. It doesn't get as hot as the original 3.6K did. It doesn't make the Zener have to drop as much current. There wasn't as much current in it as to be able to drop the voltage. Everything works a lot better that way. But the thing they did not have was on this side, for any type of noise suppression or noise bypass, there was no capacitor on that. So what I did was I just took a 0.47 microfarad film capacitor and put it on the back of the socket of the of the pins of the IC, and just ran them straight to ground. So there's one on the positive side, one on the negative side. So you can see that. Now these are 15 volt Zeners, but really in real life it's going to be closer to about 14.5 to 14.7 volts. It's just the way these things work. Shunt regulators using Zener diodes are notoriously not super accurate. If you want a really accurate, power supply, linear power supply, you'll have to use like an LM, chip or something like that and adjust it, and you can make it dead on. But it's not important, because as long as the voltage is above your maximum swing voltage that you need for the circuit, it won't matter. Even if they're a little bit imbalanced, it still won't matter. Mine turned out good. I'm right dead on about 14.7 volts, positive and negative. Just worked out that way. I put new diodes in there and new resistors that have pretty tight tolerances and don't drift with temperature or anything. And so it's pretty solid. So that's the input circuit. When we get to the voltage amplification or VAS stage, okay, that would be this right here. So you have your bias transistor, which is your, it's a VBE multiplier. Let me drink my coffee. And the VBE multiplier is kind of it's a better circuit than just using dropping diodes. You can also put a series string of diodes in here to get the voltage drop you need to get the proper bias spread, and then finish it up by putting it in series with a pot like this. But this VBE multiplier is kind of a more elegant design. This is mounted right on the heat sink in between the big output transistors here. And this, not only does it provide your bias spread that you need between your two drivers here to overcome that turn-off range, that forward voltage drop of the transistors, but it also allows it to thermally track. So as these transistors heat up, they will heat this up. As this heats up, the VBE will change. As the VBE changes, it will compensate for the bias drift that you're going to have, because as transistors change their temperature, their VBE will change. And when the VBE changes, the gain of the transistor changes. It's a moving target. This counteracts that. If you use the correct type of transistor and circuit, it will keep this thing in line. And that's what this does. So the original one was a little TO92 type transistor, and if I have it here still, I'll show it to you. Yeah, here's one. It was this. And these are getting really hard to find now, and when you do find them, they're kind of overpriced for what they are. They're just a transistor, but these have really high gain, and on top of them, which isn't a big deal for this circuit, the gain really isn't a huge factor in a VBE multiplier circuit. But this has that little heat sink on it. Now, I'm sure you could make this with a piece of aluminum strip, and bend it around a modern transistor. But this TTC004B, which is in a little square, what is it, TO126 package, I think that's what that's called, it fits right in there perfectly, and it worked out really well. So that's what I used. There's probably other ones you could use, but this one is good for 300 volts, for the VCEO, and that way, this is a relatively high power supply, so you do want something that can handle that. That was another factor in this. It could take that kind of voltage. But anyway, drop-in replacement for that. On the negative feedback right here, I put this 10 picofarad capacitor around here, and thank you to one of you viewers. Tony was having a wheel was turning but the hamster was dead moment, and I tried to put a capacitor from here to here to see what it would do, which it didn't do anything. But you're really supposed to put it across your feedback resistor like this. And what that's going to do is, let's say this amp oscillates at high frequency. This is a high pass filter, so at low frequencies, this is not there. It acts just like an open circuit, and all the current flows through the resistor. At high frequencies, it bypasses this resistor and goes through this capacitor like it's a dead short, or like it's a smaller resistor than this, depending on the frequency. It changes with frequency. And that's going to feed back in here. So at really high frequencies, it's going to have basically like directly connecting here to here. So it's going to cancel out your input. So the whole idea of that is that's going to remove or vastly reduce anything you get from parasitic oscillation. If an amp goes into oscillation, that's what kills the outputs, that's what kills your speaker, all that sort of thing. So we want to prevent that. That's what this does. It can easily be removed by just heating it up and popping it out. So it's everything in here is reversible, if you notice. Looking at the bias circuit, one of the things I noticed is this transistor ran warmer than it really needed to run. You want it to run a little bit warm because you want it to get to an ambient temp, like a stabilized temperature, and that again makes you have a stable VBE. You don't want it to run ice cold all the time because then as you drive it and it heats up, it'll change and your bias will get messed up. So, but in the same token, you don't want it to run so hot that once you start driving a signal through it, it gets really hot and eventually it will wear out. The transistor will start to fail. So I've tinkered around with this a little bit. And what I found out was that this was, I forget the original value of this and this. I'll try to post it up, but they were a lot lower. This is your tail resistor, or this is kind of like a current limiting resistor, let's call it. And it's a voltage divider. This is a kind of an interesting circuit the way they did this. This is what feeds current through your bias spreader and through your voltage amplifier stage. Okay, so just kind of look at that as a straight through between your positive and negative rail. Don't think of this as ground. Just think of this as, you know, this is your negative, this is your positive. Okay, and that's how this circuit is seeing the voltage supply. And this will control the current going through there. So by increasing these values, I reduce the amount of standby current in this. Now you don't want to go too far because as this drives signal through here, you want to be able to provide enough current for this thing to act properly to drive the outputs. But when it's sitting idle, you don't want it to sit there and just heat up the transistor. So I played around with this and I was able to get 12K at 4 watts and a 4.7K at 1 watt, and combined that gave me a really good quiescent current through this circuit. Now, why didn't they just put one resistor in there? Why 2 different resistors in series? Well, if you look, there's this weird looking capacitor here. It's 47 microfarads at 100 volts, and it is an electrolytic cap. And if you look, it goes at the junction of this. So this is kind of like acting like a voltage divider. Not to here, but to this point it is. And this capacitor goes back here. It doesn't go to ground. It goes across here, and it goes to the output of your driver, and which is the input or the basis of all your outputs. So what's happening is as you drive this driver transistor and the voltage goes up here, that feeds back through here. And that makes this either more or less positive depending on where this point is. And it actually will change the voltage drop of this circuit. It's a feedback circuit. That's what it is. And it's a feedback circuit that affects your voltage amp stage. So that's going to bypass this partially. So that's what that is. So why am I saying all this? It's really, really important that we get the proper ratio of this to this, because you want this voltage divider to stay the same. So even though we're changing the current in this circuit, this voltage drop ratio has to remain the same so that this value of capacitor can do its thing. And that's what this is. 12K and 4.7K is going to give you the same voltage divider as the original resistors. The other thing is this transistor, which is this 40412 44, it's an RCA. You can see it's just a little TO5 case transistor, but it's got this gigantical heat sink on it. It's not even aluminum, it's a steel heat sink. This is a really good transistor, by the way, but they do go bad after a while. The gain will drop on them. So I replaced those with a KSC 3503. These are very readily available. They're very common. They're inexpensive. They're easier to heat sink because I used one of those little adapter boards, and you'll see this when I show you the finished product. So this is very easy to replace now if it fails. And it also can spread the heat out better because instead of being against the board, you don't really get that convection because this was mounted flat on a board. It has a heat sink on the side, and so the air can convect up, and it should be able to regulate the heat on that transistor a lot better. Moving over to the pre-drivers and to the overcurrent protect circuit, I left all this alone for the most part. If these are bad and you can't find these, the ones that were in there originally, which is the FPN 3569, you can replace these with a 2N5551 and a 2N5401 if you can't find those original ones. Now your divider circuit that controls the input of these overcurrent transistors. So what these do, you can take these out of the circuit and the amp will work perfectly with them not even in there. The purpose of them is they stay out of the way and don't bother anything until the voltage drop across this resistor or the voltage drop across this resistor gets too high. If this voltage drop gets too high, that means that there is excessive current flowing through that resistor, right? So what's going to happen is that voltage will get high enough that it'll turn on this transistor. As this transistor turns on, if you noticed, it's going through this dropping diode or the steering diode into the base of your pre-driver. So what it's going to do, it's going to take this and it's going to bypass it straight to the center point, which is ground through your speaker, by the way. So essentially what it's going to do is it's going to block the input of this, which is going to reduce the signal in here. So as you get an overcurrent, this will start to turn off and you'll start to flat top the waveform. It'll look like clipping, but it's not really clipping. It's artificially induced clipping to prevent an overcurrent situation. That's what these are. This circuit's been around for a long time. It's used in a lot of different things. You know, even the old Macintoshes, a lot of them, they give them names and fancy names, but it's an overcurrent protect. One is for the positive going half cycle. The other is for the negative going half cycle. Now this shunt circuit prevents this voltage from getting too high. So what would happen if this transistor would dead short and then this resistor would blow open? What would happen is your 100 volt DC rail would go into here and you'd put 100 volts right across there, which would just smoke this transistor. So what they do is you have a 180 ohm resistor and you have this little pull-up resistor, this 56K, and then you have this 3.9K, and then you had a 1N4148. The problem with the original circuit was when that happened, and it does happen sometimes, these short, all that, if you did the math, you would be dissipating a lot more power into these resistors than they were rated at. They were only little tiny half-watt resistors. Let's see if I have one. Yeah, here's one. Here's one of the original 3.9Ks. You can only see the three, the white band is missing because it's all brown, it's cooked. And that's what would happen. If this would short, it'd burn these out and you'd still trash this. So what I did was I changed these to metal film, first of all, instead of carbon film. And I increased them from half watt to 2 watt. So you have a 2 watt 180 ohm and a 2 watt 3.9K. And then I increased the 1N4148 is a high-speed switching diode, but it's only good for a couple hundred milliamps, which again is not sufficient for this. So I put in a UF 4004, and that looks like a 1N, 4007 or something like that, but UF stands for ultra fast switching, and the 4004 is a 400 volt reverse voltage, maximum breakdown. So this is much more robust, and it will still react the same way as the 1N4148 for this circuit's purpose. And this circuit is more robust now. So what will happen is if this dead shorts, these will get hot, but they won't burn up. They're lifted off the board slightly for air to get around them, so it's not going to damage anything. And it'll give you time to find out that something's wrong. Hopefully this fuse blows or something like that, but until that happens, that'll prevent this from burning up. That's why I made these changes in here, and I did it to both sides. Down here in the bottom, in the previous videos, I described all this. I described it in the 400, and I described it in the earlier parts of this series on the 700. But I added the input current limit, inrush current limiting circuit. And all it is an inrush current limiting SL32. And this one's rated for like 40 amps continuous, and I forget how many amps surge. And then a relay to bypass it. And that relay, as you can see, there's a 9K 5-watt resistor, and it goes directly up to here to your B+. So as this thing turns on, it's charging through this ICL because this contact is open. The high current is being limited by this inrush current limiter, and this begins to heat up. As it heats up, its resistance drops, but then it gets hot. That's the problem. A lot of people will just leave this in there, and this thing will get really hot, and it'll put heat inside of your amplifier. And then as this charges up, once this voltage gets high enough to pull in this relay, the relay pulls in and it bypasses this. So it's like this is not even there. This becomes a short. So this doesn't get hot. Very nice circuit. If the voltage, if you turn the power off and back on, this will stay in because this capacitor is still charged. But if you turn it off for a while, once the voltage of this drops below the pull-in on this will open. So then when you turn it back on, it'll limit the inrush. But if it's already partially charged, this stays in. So if you turn it off and back on, there's not a whole lot of inrush current. So this doesn't need to come out. It's very simple circuit, but it's actually pretty cool how it works. So that's what this is. And these capacitors were increased to 150 volts. When I rewired this thing for 120 volts from the 240 that it was originally came to me as, that 90 volts or so they said it was actually more like 103 volts, which exceeded the 100 volt rating of the capacitors. And so I went with 150 volt, 11,000 microfarad, and they were pretty much drop-in replacements. They fit right in place of the old ones, and the part number is down here. And I went over this in a previous version or previous part of this video series. The originals were 9,800. This one's 11,000. The capacitance really isn't a big difference, but the voltage is. So, and these are really, really good capacitors. These are used for computers and things like that that have real high current and so forth. And these are pretty low ESR also. Now moving over to this is essentially untouched. I replaced these carbon resistors with metal film, but other than that, the wattage and so forth and the resistance is the same. It's all factory stock. You can see they already were using 1N4004s here instead of the UFs. See that? And then I increased these bypass caps that were in there. We talked about bypassing your power supply. That's what these are. They were already there from the factory, but they were originally 0.47, and these are 1 microfarad, 250 volt film. So I just increased that a little bit because I had them. Those green capacitors that were originally in there, the original 0.47s, those will sometimes, not always, but sometimes that epoxy that they're made of will crack. It'll dry out and crack and they go bad. So just for future proofing, I replaced them with these. The transistors, I had shorted transistors. We did the testing on them. You saw that. So I replaced the whole set, and for the NPNs, I went with MJ21196, and with the PNPs, I did MJ21195. So that's why those were changed. And those are pretty much a drop-in replacement for the originals that were in there. And then on this end, we added the speaker protect board. This is like an off-the-shelf thing you can buy from eBay or from Amazon, a lot of places, and I went into that before. And I added this little snubber circuit. I rebuilt the Zabel network with new components, kept it the same, and then I added this snubber circuit in here. This actually protects the amp from the speakers. If you have a set of speakers that have a really complex crossover in them with lots of capacitors and inductors and things, a lot of stuff can happen here on the load that it presents to your amp. And one of the things you could have is you could have little oscillations, little bursts of high frequency and so forth. This will suppress that. That's its whole point. Normally it looks as, this is a thick piece of wire, this coil. It's only 22 turns of number 18 magnet wire, solid copper. So normally it just looks like a piece of wire. It's like having an extra length of wire in line with this. But as you go up in frequency, like if you have parasitic oscillation, it will act like a high resistance. And then the voltage, the signal will be, more of it will pass through this 10 ohm resistor, which this resistor will suppress the current. It will reduce the current. So it's just a protection circuit that doesn't really act like it's there at all unless something that's out of the audible frequency range happens here that you don't want. That's what that's for. And that's a homemade circuit, and I got into that in an earlier part as well. So that's the whole circuit. This is what it looks like in its entirety, and those are why I did the changes that I did. Now let's take this thing, I'll go back to my original recordings and we'll pick up where we left off. Okay, here's the board. And again, you can see where I used these transistor adapters. And I'll get one out that I use. And it's just, these are little, you can make this out of a piece of proto board or something and like just use some little wires and make them yourself. But essentially the TO5 transistor is this side, and your TO, what is that, 214 or whatever that case style is, these little ones, they plug directly in here, and it just makes sure that pin for pin they line up. So you can either put a TO5 in here and put 3 pins in and it'll fit in place of these square ones, or you could put the square one in here and put 3 pins in and it'll fit in place of the TO5 case. So it's just a little adapter board. And you can see where I used them. I use these little 87-cent a piece at DigiKey heat sinks, and I posted the part number for those on the previous part, so you'll have to go back and watch those other parts. And these ones I used a little bit wider because I had more space here. Same adapters, same kind of transistors. These are KSC 3503s. These NPNs are KSC 3503s. And the PNPs are KSA 1381s. So these are KSA 1381s. The rest of the transistors are pretty much the same. The bias transistor, which is your VBE multipliers, those are down under here on the heatsink. I used the TTA004B Toshiba transistors in place of those TO92s with the little folded piece of aluminum heatsink on them. These are much more robust. They couple to the heatsink a lot better, and they have a little bit different curve of temperature versus VBE, and it actually is advantageous in this circuit in that it really keeps these transistors under control when they start to heat up under heavy load, and end up working out really well. So that's what I stayed with. The resistors are larger. Again, I told you which ones I changed values on, but you can see these 4 here and these 4 here are higher wattage than the originals for the reasons that I shared with you. The 10-turn bias pots are right here, and it's really nice. You can just take the bottom cover off. You can connect to the test points right under here, and then you can adjust your bias without taking all this apart. It's real easy to get to if you need to. The speaker protect board is over here, and you can see the Zabel networks and the little snubber networks are all over here on their own little terminal strip. It all fit in there very well. I put some new banana jacks because the old ones were really kind of they were tarnished and they were not tight anymore. Same thing with the RCAs. I had to put some new RCA jacks in because the old ones were just too loose. I would plug in an RCA plug and the signal would drop out and you'd wiggle it around and it would come and go and cause noise and all kinds of stuff. So just took those out and just drop in replacement, a new set of RCAs. There's the switch, just a cheap little slide switch to go between the capacitor coupling and the direct input coupling. And I cleaned that very well and put some deoxit on it. And Bob's your uncle. That's it. So there is the amplifier in its completed form. I'm going to put all the covers on and put it together. I can't really lift it or anything. I'm not even allowed to push or pull over 10 pounds. So I'm probably not going to be doing much with this other than I'll hook it up for you and I'll let you hear the how it sounds. The distortion figures on this thing were astounding. They were down in the 0.01, 0.03 range, which is what the amp was originally rated at, by the way. At 20 hertz, it was a little higher. It was more like 0.1, but still, that's pretty good. Setting the bias on this is a little bit tricky. I'll talk about that for a second. In order to properly set bias on this amp, you can go across these little 10 ohm resistors. You can see, let me see if I can show you one down here. They're hard to see, but I'll kind of zoom you in. Here's one of them. There's 4 of these in there. Actually, there's, 4 of them, 2 on each channel. This is your 10 ohm resistor, and this is the emitter resistor for the driver transistor. So these 4 transistors on this end of the amp, this one, this one, this one, and this one, those are your drivers. Then these below there, 1, 2, 3, 4, 5, are your outputs, okay, for each line. This resistor that I showed you is the emitter resistor for this transistor driver here. Even though they're mounted up here, it's kind of weird looking. That is how they are connected, okay? They're also connected to the base of all the other transistors. So you can see they're all tied together here. It's kind of confusing if you don't understand what's going on. That you're measuring across this 10 ohm resistor to set your bias, and the instructions will tell you to set it to somewhere between 0.3 and 0.4 volts, or 300 and 400 millivolts. This amp, the way it is, if you do that, it will work. But the amplifier will not have as low of a distortion figure as you can get. It has to be a little higher than that, at least with these new transistors. I ended up being closer to 500 millivolts, anywhere from 480 to 500 millivolts. So it had to have a little higher bias. The amplifier doesn't seem to idle warm at all at that level with this, so I'm not worried about it. But that's where it's set right now. And the way I did that was I connected a distortion meter to the output right at the terminals here directly. Connected an 8 ohm load and then began driving the amplifier with a 1 kilohertz signal or whatever I wanted to measure the distortion at frequency wise. And then I started adjusting this pot until the distortion dropped to its minimum. And then If I moved it more and it didn't change the distortion anymore, I went back up until finally the distortion would just start to creep up again. And right at that breaking point there, that's where I left it. And that's the best way to set bias on this amp. Now, as I was saying, the frequency linearity, frequency response and everything was very good on this amp. Now, it's flat from 20 hertz all the way up to 20 kilohertz and a little bit beyond on each side. It starts rolling off at 20 hertz and starts rolling off a little bit above 20 kilohertz. It goes up pretty high. And that's where it is. So I'm going to put the covers on it and we'll take a listen to it. Okay. Well, I have this thing all put together now. Everything's put back together. And I have my microphones in stereo mode because I'm going to set them up with the speakers. And we're going to listen to our Stranger Danger. Seems... Well, and there you have it. Another project done. And I'm going to take advantage of my son being home today to visit. And I'm going to have him lift this thing off the bench and get the next project up here. I have quite a few things backlogged to do. I have enough projects probably to go for 6 or 8 months. My neighbor came over yesterday and asked if I would do a project for him. He and his son are both really into classic cars, and they have some really nice ones over there. And they're doing a stereo install kind of from the 80s type, era. And they have an Alpine stereo, a vintage one, and want me to service it and take care of the couple issues with the cassette player and so forth. So that's less than 10 pounds, so I can lift that. So maybe I'll have him bring that over, and maybe that'll be a quick project that we can do on the bench. And I have quite a few other things I'd like to do. And like I said, I have a couple ideas for some other short videos I want to do for some test equipment and things like that. But let me know if there's anything specific that any of you want that I could do, just short videos. So anyway, that's it for this one. I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again in the next round here. And until then, stay well, everybody. Take care. Bye-bye.